Okay, so we're going to graph these things called quadratic functions. We're going to use that often as we go through here. A quadratic function is, we'll define to be a polynomial function. So it has all the characteristics of polynomials we had from last chapter. Can't have negative exponents on variables. Can't be dividing by things. Variables can't be in the exponents. It's a function that looks like a polynomial whose degree is 2. The second degree polynomial. So it's kind of like in this general form that's up here. It's got an x squared. An x squared is its leading term, and it can have other things added or subtracted to it. But in general, they just polynomial degree 2. The graph of a quadratic is called a parabola. Okay, so we're going to start by graphing these quadratics, kind of some pretty basic ones. The most basic one is called the parent quadratic function, and its equation is this guy.
Oh,
Y equals x squared. This guy is the parent function. The parent. It's called a parent function because we're going to base all of our other graphs off of this parent function. It's like the one that we're going to create everything else from. It's the most basic one that we'll get others will be based off of this original guy. Its equation is y equals x squared. It has a table of values. One way to write is a little table of values. Recall when we write table of values, we get to pick the x's we want, and then we plug in x's to figure out y is. So like we'll generally do like these 5, like we did for exponential functions. And how am I going to come up with y's here? Well, what's the rule to get y? Plug the x in, or in this case, square it. So what's negative 2 squared? Negative 2 times negative 2 is positive 4. What's negative 1 squared? 0 squared. 1 squared. 2 squared. 4. And note all these little points around here. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, positive 4. So on. This is going to be pretty important, the table of values. We're going to use that a lot. Just for giggles, if I put a 3 here, what would the y go with 3?
9.
3 squared is 9.
16.
4 and 16. Well, that looks like all those perfect squares that I've been telling you to memorize for a long time.
49. 64.
Okay. Okay, so every parabola has 2 very important features. The first is a vertex, and that's the maximum or minimum point on a parabola. Notice a point. So if I ever ask you for a vertex, it better be something comma something else. What does it look like? The vertex is kind of like, if you want to think of this in terms of like visual, the vertex is like the peak or the valley of your parabola. If you think in terms of like mountains or
vertex,
sort of thing.
like vertical.
You'll see the word vertex used a lot in math. They're usually used for like important points. Like you see like the vertices of like triangles are like the points, like the edges of the triangles. the vertex of an angle in geometry is like where the two sides of the angle meet up, that point. A vertex generally is an important point. So on our parent function, the vertex is this arrow pointing at it right here, which is at 0, 0. Is the vertex of our parent function.
But we call the vertex, not the vertex.
Let's see. The axis. The other important piece is the axis of symmetry, and I think Nate hit on that just a second ago. And that if you notice like the graph, this graph is pretty symmetrical. It's like mirrored across. Axis of symmetry is the line that divides
The y-axis.
the parabola into symmetrical parts. In our case, you're right. In our parent function's case, it's this line. Axis of symmetry. And it has an equation since it's a line. Our axis of symmetry for us will always be a vertical line.
I can help you with that.
If it was horizontal, then that would mean your parabola is turned sideways.
We're not going to cover that.
And we're not going to do sideways parabolas in this class, yeah. So for us, for vertical parabolas here, it's going to be a vertical line. And all vertical lines are an x equals equation. So then what should the equation of our axis of symmetry always look like?
X equals.
This will always be an x equals equation. So when I ask you coming up here to identify the vertex and identify the axis of symmetry, you better at minimum be giving me a point for the vertex and then an x equals equation for the axis of symmetry as we go through. So then what's the equation of the parent function's axis of symmetry?
0, 0.
The vertex is 0, 0. What's the axis of symmetry's equation? Nate? X is 0, and then y can be anything. Okay. Okay, so we're gonna graph the first example down here, and then identify some parts and do some comparisons and stuff to go along with it. If you have nothing else, you can always graph this like we did exponential functions earlier, like you graphed lines all last year, which is to make a table of values. So we'll start there, and then we'll try to maybe find some shortcuts once we got the table of values made up. So how about, let's see, for our first one here, we'll make an x and y table. I get to pick my x's, so I'll pick kind of standard x's here.
Quick question, Mr. Fisher.
Yes, sir.
When did we get our test back?
So I'll make a table. Then we'll plug in these values. So let's see. So to get the y's, I'm gonna plug it in to my function here. So the first one will be 2 times negative 2 squared. What's 2 times negative 2 squared? How do we evaluate that?
Negative 2 times negative 2.
We do the exponent first. Negative 2 times negative 2 is 4. 4 times 2 is 8. Well, 2 times negative 1 squared.
Well,
Exponents first. What's negative 1 times negative 1?
1.
1 times 2.
0.
0 squared is 0. 0 times 2 is 0. 2 times 1 squared.
And then 8. Oh.
2 squared is 4. 4 times 2 is 8. Okay, so again, we pick some x's that we want to check out. Again, 0 and then some on either side. Then we'll plug in x's into our function and come up with the y values. And let's graph them. So let's see. Negative 2, 8. Back to up 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2. 0, 0. Over 1, up 2. Over 2, up 8.
Oh, I hate going through it.
Okay, so then we'll draw a nice smooth curve. Connect the dots. We'll continue drawing a graph, arrows, so it keeps going on forever. One thing you won't do, because it annoys your math teacher and it's just plain wrong, is that when you get to, once you've graphed a couple of these, you won't take your pen and draw your line going straight up a line.
Why did you
Because your parabola keeps getting wider. You can keep plugging more x's in, so it does keep widening out. It does not go straight up the line, which is what people love to do for whatever reason. Don't draw yours going straight up the line, because it doesn't go straight up the line. It keeps widening. Okay, so I've got this. Okay, I need to compare this. Oh, before we do any comparison, where's the vertex?
0, 0.
Right here. At 0, 0. I abbreviate axis symmetry as axis of symmetry. So where's the axis of symmetry? What's a vertical line right through the vertex?
Y equals 0.
It's an x equals something equation. And what's x equal?
Anything.
Anna? Something to note is that whatever the x value of your vertex is the same number that x is equal to in your axis of symmetry. Because your axis of symmetry always goes right through the vertex. It's an x equals equation. So whatever those two numbers are, they're the same. Okay, so lastly, let's do some comparing here. I know you guys love doing comparisons. Do you remember some of the comparison vocabulary we used back in chapter 8 when we talked about exponentials? Mirrored, we used a better word than mirrored. Reflection. Okay. Is this a reflection?
Yeah.
Well, so what are we comparing it to? Y equals x squared. What's y equals x squared?
Well, we're going to have to do it, which is why I hate it.
What is y equals x squared?
Oh,
The parent function. So when I ask you to compare it, I'm asking you to compare the graph we just did, always going back to the original parent function.
I
So
believe it.
how are these the same? Well, they're both parabolas, and that's good. How are they different?
But
How is this one compared to this one?
2x squared is stretched.
It's stretched out. By how much?
I don't know. That's 1. 2.
How much is this stretched out by? How much is this stretched out by? You could maybe compare the table values.
2.
This one's double this one, so it's stretched by a factor of 2. Without comparing those two, what's another way you could have came up with 2 as what's been stretched by Nate? It's more spread out. Like I said, it's asking like, how do you know how much more spread out? Without even comparing those two tables, you could get that number by figuring out what's in front of the x squared.
Whoa.
Okay. So we made a table. We found the vertex. We found the axis symmetry, and then we compared the function to its parent. These are things you're going to be asked to do often throughout this section here, and certainly on the eventual quiz we'll take, which will be next week. I want to do the second one, but I don't want to spend all the time. I don't want to go through this process of plugging in and getting a table. I want to make my table really, really fast. So we're going to figure out, I have a shortcut to do. So a shortcut for coming up with like the second graph here without having to plug in each of these x values into the function and doing like this stuff we did before. Exactly what Nate said. If you know the table for the parent function, then you can get our new table just by multiplying all the y's by what's multiplied to the x squared. So using the Nate method of a quadratic table of values, what should the y value be with -2 in our case? What y value should be associated with -2? It should be -4 times 4, which is exactly -16. What goes with -1 then? -4 times 1. What's -4 times 0? What's -4 times 1? What's -4 times 4? You need to keep going. Okay, so we're going to graph this thing. Oh boy, -16 is going to go way off the charts here.
I hate the ones where it's not forward.
So if it goes so far off the charts, we won't graph it then. We'll just leave it go. So, okay, so you could count by 4s. All right, fine, we'll count by 4s. So if I'm going to count by something other than 1s, I got to label my axes very thoroughly, though. So what I mean by that is I'm going to count by the y's by 4s. I better make sure that I know this is 4. That's 8, 12, 16, -4, -8, -12, -16. So it's not so squished horizontally. Let's count by 1s horizontally. So if you're going to change the scale, you got to put a little extra work in here to make it happen. But we can do it. Now it's a little bit easier to graph though. So 0, 0 still right here. -1, -4. Back 1, down 4. -2, -16. So back 2, down 16. Over 1, down 4. Over 2, down 16. Okay. Where's the vertex at?
Yeah.
What's the axis of symmetry? Okay, we got those two. Okay, how does this compare to the parent function? Okay, so let's be careful. This will not be a shrink.
It is stretched.
Okay, so if you remember from when we first started doing the comparisons, the negative sign was kind of its own separate thing. We compared the stretch and shrink by just the what's called the absolute value of the number. So it's a vertical stretch by the absolute value of this, or the positive number of this, which is 4. The negative does do something else to it, though. What's the negative do?
Flip it.
Okay, it's flipped it upside down. So what's our terminology for flipping it?
Reflected.
And it's a reflection.
That means on our homework we get the graph.
Okay. Yeah, so your homework is going to be almost all graphing. With any luck, these shortcuts will make graphing easier, though. If you know the parent function, then graphing goes really fast. If you don't know the parent function, and you don't take any time to learn it, then graph's going to be a pain in your butt. Just all there is to it. Learn the parent function, and then life gets a lot quicker. Because then you can handle just about anything else I can do to you. Like on the backside.
Parent function's easy because they're just perfect squares, correct?
Yup.
Oh,
Okay. So what happens now if I throw a fraction in front? Well, fraction is numbers. So if I want my table of values,
175 and 1.
so I give you my table of values, what y goes with -2 now? Well, how do we find it? What's the quick way without having to plug everything in and all that stuff?
Multiply it by that.
Why don't you multiply every y that goes with its x by -1/2?
Be 1.
So what's -1/2 times 4? What's half of 4? Half of 4, and the negative is -2.
Whoa. Hold. What?
Right? Because what value goes with 2? What y goes with 2 in the parent function? 4. So what's -1/2 times 4? -2. What's -1/2 times 1? -1/2, or -0.5. Okay, what's -1/2 times 0?
0.
What's -1/2 times 1? -1/2. What's -1/2 times 2 squared, or 4? -1/2 times 4? -2. Okay, so I graph all those. Let's see. Back 2, down 2. Back 1, down 1/2. 0, 0. Over 1, down 1/2. Over 2, down 2. Draw my parabola. What's the vertex?
0, 0.
It's right here at 0, 0. What's my axis of symmetry?
X equals 0.
How does this guy compare to the parent?
It is vertically and a reflection.
By how much?
Oh, half by 0.5.
And It's a reflection. Okay, most of you are this far. We got, let's see, X and Y. If we do our normal, should get 4/3, 1/3, 0, 1/3, 4/3. What do you think? What do you think 3 would be? What do you think 3 would be here?
Hold on. That's crazy. 5/3.
What would 3 be? What's 3 squared?
9.
So 9 times a third?
3. Isn't it?
Yep. So it would be 9/3, which is 3. Anyways, so we can graph 0, 0, -1, a third, -2, 4/3.
What are you talking about? He just showed.
So something like this. How does this compare? This is a vertical shrink by 1/3. 1/3. Okay, so what else can we do to this? How about these two down here? Oh, you could, the vertex and x symmetry are both 0, same as before. Graph the function compared to y equals x squared. Okay, what's going on in this function that's different than the other ones we've seen?
You're adding 1.
Jordan?
Well, actually, I was going to ask you this.
Oh, well, we're adding 1, but yeah.
Well, so for the other one, this question, but
Anyways, we've added 1. So, what do you think the table of values that we're going to make is going to look like? How are we going to adjust our table of values from the parent function?
add 1.
Add 1 to everything. So if you know the table of values of the parent function,
5, 3, 1, 3, 5.
the original is 4, add 1, it's 5. Used to be 1, now it's 2. Used to be 0, now it's 1. So we'll take so all these, our graphs should look something like, this. What's the vertex?
0,
1. X is 0, y is 1. What's the axis of symmetry? X is what?
0.
0. So those two things are the same. I don't have a spot for comparison. What's the comparison here? So, is this stretched at all?
No. Oh, what's that word? Where you use the slide? Slid. Boom.
Okay, you could slide up by 1. A better terminology, a more technical term would be this is translated.
Oh, I like slide much better.
Up.
Will you mark us off wrong?
No, if you use either, I'm okay with that.
I mean, slide.
Either one's fine.
Stop.
Okay, here we go. Now we get a big one. We have both a fraction in front and a number to the end. So, what are we going to do? We're going to multiply. If we want to make table values, you'll figure out your x table values by doing the multiplying first and then take away 2. So if you have your table of values, so what y should go with -2? Well, it would be the y that would normally go with it times 3/4, take away 2. So what y goes with the parent function at -2? 4. So what's 4 times 3/4? What's 3/4 of 4? 12 over 4, which is 3. And what's 3 minus 2? 1.
How do we do that? That was a lot.
Okay, again, I took what the value I get in my table for the parent function. For -2, the parent function is 4. So I took 4, multiplied it by my number here, 3/4, and then added -2, or subtracted 2.
Wait, but isn't 4 minus 2 2?
We have to do the multiply first and then subtract.
So,
So 3/4 of 4 is 3. 3 minus 2 is 1.
oh, tricky.
Okay, what's 3/4 of 1?
0.75.
0.75 or 3/4. And what's 3/4 minus 2 or 0.75 minus 2?
Well, we have to find a greatest sum.
Take it away. -1 and 1.25.
This one will be -2.
And then it's actually mirrored, which is nice. So let's see, 0, -2, -1, -1 1/4, 1 1/4, 2, 1, 2, 1.
Wow, that's what? Oh, I did that wrong. Yep.
What's the comparisons here? What's multiplying by 3/4 do?
Shrink it. Reverse.
What's subtracting 2 do?
Slide it by negative.
Slide what way?
Down by 2.
Where's the vertex?
Oh, -2. 0, -2.
Where's the axis of symmetry?
0. Easy.
Shortcuts, before we go. Shortcuts. If for this equation, if what's multiplied in front of x is bigger than 1, it's a vertical stretch.
I know that.
If it's less than 1, it's a vertical shrink. By A. If you add C, if you add something that's a slide,